Hello, this is my recording for workshop one, computer algorithms analysis. So my function, I opted for something based on the context of Pokemon. Um, I wanted to look for the a good move against a certain amount of Pokemon, and you iterate through based on the trainers because you do not know how many. And this could be used for one of the mainline games. Maybe you're going through Pokemon Red and you can look up all the trainers and their Pokemon. And if you plug that in, this would help you figure out which move is the most effective based on the average time it is effective. So what it needs is a list of moves and a list of trainers that contain a list of Pokemon. And it'll use a type effectiveness chart that I remember making in CSC 275 in order to figure out the damage multiplier calculated for a move. So here's my pseudocode. You can see on the right hand side. And this went through several reiterations. I messed up. I tried another one, which would not work because it would run linearly rather than what this one does. And this could probably be expanded. The only factors that are being considered is whether the move is effective or not. It doesn't account for the power of the move, whether or not it gets a stab bonus, or maybe the move is special or physical, which, when paired up to the defense of another Pokemon, would deal different damage. And then for the inputs, we have moves, which is a list of move class objects. And we assume that it has an attribute named type for when we access the type chart. And then the trainers is a list of trainer class objects. And that list has a list of Pokemon. So we assume it's a list of lists and we iterate through the rows and then the columns, and each spot would be a Pokemon. And then we have the type effectiveness chart. I abbreviated it to TEC. It's a table of float values that are returned when we give it two types. And that will be whether or not a move is 2 times better, maybe half, maybe it doesn't do any damage. And then within the function, we have several integer variables: size of trainers, size of moves, and best move. For the size of variables, it's for improved readability in the for loops. They're all integers just meant to hold the size of the list. And best move is important. It is an integer that represents the position where the move is in the moves list. And when we complete the loop, we will have some spot that is the best move based on what we are looking for. And then last best tally is another integer that we use to store the greatest sum that we find. And that is how we compare which move is the best at each iteration. If it's effective, it gets +1. And if that's now the highest count that we have so far, that'll be set to best move. Move count, this is an integer array that holds just the counting value for each move. So it has to be the same size as the moves list. And I use it to sort of mirror what is done or what needs to be returned. So as we iterate, we increment different spots within that array. And then size of moves and size of teams, it's just the integers that hold the sizes for the moves list and each Pokemon team that a trainer has. This also accounts for the possibility that trainers don't have 6 Pokemon or 1 Pokemon, or they have just differing teams. And then the modifier variable is a float value that stores the damage modifier returned by inserting the move type and Pokemon types into the TEC. So for the preconditions, we expect that the length of moves will be at least one or more. Otherwise, there'd be no point to running the function. And it would be preferable if the moves were organized in descending order based on move power, because whatever is the first highest value will be the chosen one despite the next one having the same value. So for the case of a tie, it'll always be the first pick in the list. So if someone wants to make better use of this algorithm, then I recommend this. And then we also assume that if the Pokemon has only one type, trying to compare the second type in the type effectiveness chart will return a 1 so that it's only affected by the single type, not a non-existent double type. And then for the post conditions, the best move is equal to the position of move count, that it has the greatest value. So this is just a bit of an iterator that holds the position for what is currently the move that was the most effective so far. And then if there's a tie, it's the first one. We started at 0 because at that point, you haven't seen anything yet. So first pick is the best pick. And then the function returns a move found from the moves list. And you'll see it again in the code right here. Returns moves, best move. And now if we look at time complexity, you can see on the right-hand side that I did the math similar to what we did in class. And I decided n would equal the length of the trainers list, p would equal the length of the trainers list at each row, m would equal the moves list length. And when we do the basic combining of these, you can get the statement big O of m plus big O of n times p times m plus constant time. But we have to consider the rules of Pokemon. The size of a team can only be up to 6, or it can only be as little as 1 Pokemon. So this for loop is bounded, and it would count as a constant. So when we look at the worst case and the best case, we just don't have to consider it because it doesn't scale like the rest of everything else. So in the best case, each trainer could have maybe 1 Pokemon in their team. And when we do the math to simplify our statement, we would end up with big omega n times m. And I did a bit of further speculation. Since n can be equal to 1, the best case scenario would be m running time. So if there's only 1 trainer, then you only iterate through that trainer's team, and then you find which move is the most effective. If you only have 1 move as well, then the algorithm would probably run constant time. If there's only 1 trainer and 1 move, it'll just run through everything once and then return that move. And then in the worst case, each trainer has 6 Pokemon maybe, but that is also just a constant that we can forget about. And when we simplify it down, we get big O of n times m. And so it is possible for us to turn this into maybe a squared if n and m are equal to each other. But if one is greater than the other, then I assume we could bound it to as much as a cubed, because it would just be like if you had n times n, but n was plus some constant. But since there's no real indication of what the input will be, it's hard to make an assumption on whether it'll run constant time or whether it'll run maybe at most n cubed. So what we came up with before was fine as is, and I think we could create a tight theta bound of big theta n times n, because there's nothing that'll cause the loop to end early. It must iterate through every trainer, every Pokemon, and every move. For the space complexity, um, let m equal the length of the moves, because we have to allocate enough space for an integer array has as many integers as there are moves in the input. Everything else is just constant, like maybe we have int. Um, and then further, if you wanted to try and be more efficient, maybe some of these variables could be declared beforehand, so they're only reassigned later. And what I came up with is, so at the worst case, at the best case, it will still just be m. So this is also a tight data bound of m. And then for the loop invariant, I'll state this to be true. The variable best move will be equal to the position of the first move that was effective the greatest amount of times within the list of moves. And then I wanted to make a distinction between the loops because there are two separate loops that run one after another. Loop A will signify the first for loop, and the goal of this is just to initialize move count, because in some programming languages, if you just try to create an array and allocate space, it doesn't initialize the values. So if we were to try to continue on, we might have random values that would not be correct. So maybe some value had a really huge number and that's the most effective move when it really isn't. And then loop B signifies the main loop, which has a nested loop that nests yet another loop. This is the loop that is the one that maintains our loop invariant mostly. I don't know if we could really count loop A, but you'll see in my proofing at each step how loop A wouldn't really matter. So at initialization, we first set best move equal to 0. And at this time, this would be true because we haven't made any comparisons against Pokemon. So currently no move has been shown to be more effective than the other. So for whatever reason, if we were to end here, the first move would be a correct option. And it would be the first option, though any option would work, but with the algorithm, it'll go with the first one. Sorry about that. And then if we move on to the maintenance, through loop A, we can accept that best move will remain as is, and we will go through the first loop without comparing any Pokemon. So while this loop goes, it will remain correct as it had been correct before, and it does not change anything but ensure that loop B will also be correct initially. And in loop B, the outermost loop starts at the first trainer in the list, and it'll increment through each trainer. And assuming it hasn't missed any trainers by some iteration I plus 1 will either continue directly to the next trainer, or that'll have been the end of the list. So we don't miss out on any trainers in the list. And the same applies for the Pokemon. Before we iterate through the Pokemon team, we define the length of the team to make sure we don't miss any Pokemon. So while the first team might have had less than 6 Pokemon, if the next team has 6, we won't miss the last 3. So for if it works for the first case, it works for ith case because it will have determined the length of the team beforehand, and at I plus 1, it will have redetermined that, so no Pokemon will be missed as well. And then for the innermost loop, where we start to check each move against the Pokemon, we will get a float value that we compare to 1. If it's greater than, you will increment the counter at that spot, and then we will check to see if um, that counter is now the best tally. And if it is, we will set that equal to best tally. And then we'll also change best move to be that spot. So this is how we keep it up to date. And for whatever reason, if you were to stop at any point here, it would give you the most up-to-date, best effective move or most effective move. And if we assume that it's true up to the ith iteration, then at the next one, there are a few options that could happen. We will have to check the modifier again, and then only if it's worth adding up a new increment or a new value will we check again to see if it is a new best move or not. So at the ith iteration, we have gone through everything before I, and the last best tally should be something greater than 0 as well as best move. And at I+1, it'll have updated again. So we are working with the most up-to-date value, and there is no move that was not considered. And there's no chance that we could skip one move accidentally, which may cause us to give an incorrect choice at the very end of the iteration. So when we end up at the termination point, if the loop invariant held true through each iteration, once we get out of the loop, we will have the proper value for best move, and all we have to do is return the move based on that position. And best move will be equal to whichever spot in move count had the greatest sum. And it'll go by first come, first serve if there's a tie. And it'll work based on whatever trainers were entered in each of their Pokemon. So this algorithm came to a pretty simple conclusion. There's definitely greater greater considerations to be made. Like maybe you wanted we wanted it to return more than one move, and if that were the case, maybe you could take this algorithm and repeat it, with the exception that you get rid of the first pick you have. But I was running out of time, and I think this is the 4th version I came up with. But I'd be glad to hear any suggestions or issues that you find. Let me know. I'll make the corrections necessary and create a follow-up video as needed. Thank you.